Yes.
Okay, we'll start with acid-base balance. And what acid-base balance is doing is giving us the background that we need to go into blood gas interpretation. And that's another responsibility of a respiratory therapist, is interpreting arterial blood gas data. So you'll stick a patient in the artery. Typically it's the radial artery or the brachial artery, and you draw blood from the artery. And then once you do, you put it into a machine, and then you get a printout of the list of values. And then part of your responsibility is to look at those values, interpret them, and then make recommendations based on what you see. So if the patient's on the ventilator and the CO2 is too high, then you're going to recommend blowing off the CO2, whether you're increasing the tidal volume or the respiratory rate. If oxygenation is poor, then you make recommendations of increasing oxygen or increasing that positive pressure I was telling you about. So that's where we need to end up, and then this is the very beginning of it. So going through acid, what is an acid and what is a base? So an ion is an element that has a charge to it. So it shows hydrogen with a plus. And anytime something has a positive charge, it's called a cation. If an element loses one of its electrons, an electron has a negative charge. Oh, I thought you were talking something. An electron has a negative charge, and once that negative charge leaves the atom, then that atom becomes positively charged. So the electron goes away, positive charge. You get an extra electron, negative charge. If everything is balanced, neutral. So that's what it's showing you here. Something has a positive charge, it's called a cation, and if it has a negative charge or an extra electron, it's negative, it's called an anion. So if an electron is floating around the atom, what is the center of the atom? Nucleus. And what kind of a charge is inside the nucleus? Do you remember this from chemistry? Yeah, the protons are positive. You have the positive inside the nucleus and then the negative electrons in it. So remember that oxygen is delivered to the tissues. Carbon dioxide is a waste product of this oxygen being utilized, of this aerobic metabolism. And the CO2 needs to be carried back to the lungs for removal. So the cells produce the carbon dioxide, and then somehow the carbon dioxide has to get from the tissue level back to the lungs so we can exhale. Well, there's 3 ways that carbon dioxide is carried in the blood to go back to the lungs. And the first way, it tells you that some of it is dissolved in physical solution. It says that 8% is carried in the blood plasma and in the erythrocyte intracellular fluid. Erythrocyte is a red blood cell. So some of it's just like oxygen. You say that some of it was dissolved in the plasma. Same thing with carbon dioxide. Some of it will just dissolve in the blood plasma. 12% is chemically combined with protein molecules that have 3 amino groups. I need to draw an amino group for you. 3 amino group. All right, so it's far away, it's in the dark. Can you see this? That's considered an amino group. When you have a nitrogen with a couple hydrogens on it, amino group. So free just means that it's available. So this protein molecule with these amine groups, it's called a carbamino compound.
What you just heard was a carbamino compound.
Yes, an amine group. A-M-I-N-E, I guess, amine group. So this amine group that's in the dark, all the way over here that you can't see. What happens is a hydrogen ion will leave and carbon dioxide can hang on. So that's one way that carbon dioxide can be transported, is that it'll take the place of one of the hydrogen ions in the amine group. So usually we just say, oh, it attaches to a protein. But if you wanted to know trivia, that's what happens. So then the very bottom, it says hydrogen ions are formed by this combination. Does that make sense? You bump off a hydrogen ion, it starts floating around somewhere else, and then the carbon dioxide is hanging on to the protein. All right, and then there's a third way, and it says 80% of carbon dioxide is transported as bicarbonate, which this combination occurs mostly inside the red blood cell. So it shows how bicarbonate is formed. It says carbon dioxide can combine with water and form the combination of the two, carbonic acid. Well, carbonic acid doesn't stay together. It likes to dissociate. It dissociates into bicarbonate with a free hydrogen ion floating around. And then it shows, do you see how you have an arrow going one direction? You also have an arrow going back the other direction. So it doesn't stay in one form. It kind of combines, dissociates, combines, dissociates. Well, this reaction can occur much faster when there's an enzyme available, and that enzyme is called carbonic anhydrase. It tells you that it causes the reaction to occur 13,000 times faster than if carbonic anhydrase was not there. So, without carbonic anhydrase, you don't see this happening very much, but with it, that's how most of the carbon dioxide is transported. Hydrogen ions from this reaction will be attracted to the hemoglobin. Tells you that this reaction buffers the hydrogen ions, but I haven't told you what a buffer is yet, so you're going to have to write down the definition of a buffer. The definition of a buffer is to neutralize. And I also have it cleans or neutralizes by removing hydrogen ions from a solution. Do you want to write that down too? Okay, I'll read that slower. It cleans or neutralizes by removing, you can write H plus or hydrogen ions, whichever one helps you remember better. By removing H plus or hydrogen ions from solution. So carbon dioxide combines with water, forms bicarbonate. Bicarbonate dissociates, and you get a hydrogen ion. Well, where does this hydrogen ion go? Well, it likes to sit with the hemoglobin. And so when the hydrogen ion is no longer floating around and it attaches itself to the hemoglobin, we say that the hemoglobin just buffered the solution by taking a hydrogen ion out of the solution. So this reaction buffers the hydrogen ions. Does that fit? Can you go backward from there? Well, where did the hydrogen ion come from? It came from carbonic acid dissociating. So that's where the hydrogen ion came from. I'm going to put it all together in a picture in a couple more slides. So everything I'm telling you, I'm going to tell you again in a minute. All right, so the hydrogen ion attaches to the hemoglobin, and that makes oxygen leave the hemoglobin molecule. It says it will also bump off the oxygen molecule from the hemoglobin. So if you've got blood flowing through the blood cell, or flowing through the capillaries, comes to the tissue level, and now you've got carbon dioxide coming into the red blood cell. And that carbon dioxide comes in, there's a little chemical reaction that goes on, and you get a hydrogen ion. Hydrogen ion attaches to the hemoglobin and bumps off the oxygen. That's a good thing, right? You guys like good and bad? I remember from our review session. All right, so oxygen gets bumped off of the hemoglobin, and that helps it to go into the tissues where it's needed. So, kind of helps to have carbon dioxide, because that ends up in bumping off the oxygen and sending it into the tissue. Well, when the oxygen gets bumped off the hemoglobin molecule, it has a name, and it's called the Bohr effect. And I always look for ways to remember things. And when I think of Bohr, I think of a wild pig, a boar, B-O-A-R. And with their stout, with their noses, they bump things. My brother was telling me the story of hunting and trying to shoot one. And he knew if it charged at him, it would just toss him and throw him 20 feet. So, I don't want to say the rest of the story, but that's what I know. A boar means to bump. And then I think, okay, Bohr bumps, well, O2 gets bumped off the hemoglobin, Bohr effect. So in my mind, that's how I associate oxygen leaving the hemoglobin, is the Bohr effect. It gets bumped off of the hemoglobin. Okay, some more notes about that. During the previous reaction, there was a buildup of bicarbonate ion in the red blood cell. Well, bicarbonate doesn't just stay in the red blood cell. It wants to move somewhere where there's a lower concentration. So it leaves the red blood cell, and guess where it goes? Into the blood plasma. So bicarbonate's being produced a lot, and then it just goes into the blood plasma. Well, the fun doesn't stop there. Now the chloride ions want to come into the red blood cell because of the positive electrostatic charge that was left behind when bicarbonate left. So just think, bicarbonate leaves, chloride comes in. And that has a name, the chloride shift. And I guess this is the person that discovered it. Hamburger? No, maybe your hamburger is salty and there's chloride in the salt. I don't know about that one. So chloride shift. Chloride comes into the red blood cell because bicarbonate left. Chloride shift, or the hamburger phenomenon. Okay, now this is not the prettiest slide that you've ever seen, but I love this slide, and I'll tell you why. All right, so these two gray lines right here are supposed to show you a capillary. And this oddly shaped thing is a red blood cell. And then all of these reactions are showing what's going on inside the blood. All right, so what we're talking about is carbon dioxide being transported back to the lungs, and how does that happen? So how does this picture help? Well, it shows carbon dioxide coming into the capillary and getting dissolved in the plasma, and carbon dioxide coming in and also being carried in the red blood cell. So let's break that down a little bit more. How is it carried in the blood plasma? Well, it can just be dissolved, or it can combine with a protein. Remember I was showing you that amine group? How carbon dioxide comes in and attaches to the protein. And here you see carbon dioxide. You see the COO? That's carbon dioxide. It attached to the protein. And when it did, it caused a hydrogen ion to be bumped off. Now there's a hydrogen ion floating around. So that's one way that carbon dioxide is carried. It just attaches to proteins in the blood plasma. Only 10% of carbon dioxide is carried in the plasma, so not a whole lot happens there. All right, now let's look inside the red blood cell. This is how 90% of the carbon dioxide is transported. It'll combine with water and form, oh, it's missing something. Do you know what's missing from this? What else?
The anhydride something. Carbonic acid.
Right, so the two, H2CO3, so is it big enough on your paper to squeeze in a number 2 there? Should be H2CO3.
I can't even see it.
No? Oh, okay, so when you look at it in D2L, you'll see it. All right, so carbon dioxide plus water forms carbonic acid, and it happens a lot due to this enzyme, carbonic anhydrase. Do you want to draw an arrow to it or something, or it's just way too small to even deal with it? Too small? Yeah? All right, so carbonic anhydrase is the enzyme that makes this happen.
For that one, H, with two missing.
And then carbonic acid doesn't stay together, it likes to dissociate into bicarbonate ions and hydrogen ions. Do you remember what we said about a lot of bicarbonate building up in the red blood cell? Does it stay here? Yeah, it likes to leave. But if a negative ion leaves, what comes in to take its place? Chloride ion. The other thing is we have a hydrogen ion floating around when carbonic acid associates. So what happens to this hydrogen ion? It likes to attach to the hemoglobin molecule. Is that a good thing?
Yeah.
It is. Why? Yeah, it causes oxygen to let go of the hemoglobin. So it bumps off the hydrogen ion. No, it doesn't. It bumps off the oxygen, and then the oxygen will dissolve in the tissues, in the cells. What effect is that called?
Hamburger.
No, the hamburger was up here with the smaller. This is the Bohr effect. It bumps off. Oxygen is bumped off the hemoglobin. And then carbon dioxide can also combine with the amine group on the hemoglobin protein, and that causes another hydrogen ion to be bumped. But anyway, oxygen ends up going to the tissues. So it's a good thing carbon dioxide comes in to be transported, isn't it?
Is there animation for this online or something?
If you find it, will you share it with us? Because this is truly one ugly slide, but it's so perfect. It shows everything, and I guess one way of studying is just to redraw it. Probably when you redraw it, it's going to look a lot prettier than this too. You doubt it? All right, so carbon dioxide goes, it's traveling in the blood, in the venous blood. It goes back to the right side of the heart, and then it gets delivered to the lungs. So what happens when all of this stuff goes into the lungs? Well, everything is reversed. So now you've got your bicarbonate ion combining with hydrogen, forming carbonic acid, and when it dissociates, it goes back into carbon dioxide and water. And then we can exhale the carbon dioxide. So, should we give it a fancy name? All right, here's Haldane effect. Oxygen attaches to the hemoglobin in the lung, forming oxyhemoglobin. This makes the hemoglobin a polar buffer and facilitates the release of carbon dioxide. So oxygen comes in and pushes this reaction to go, you want to call it backwards? To the left? I guess saying to the left is better. And then we've got carbon dioxide being given off to the alveoli. Haldane. How are you going to remember oxygen? Haldane sounds like halitosis, doesn't it? Like you have breath or something. So breath is air, Haldane, lungs. I don't know. Figure something out there to help you remember Haldane effect. where oxygen combines with the hemoglobin and that forces hydrogen off, and then carbonic acid is formed, and that breaks up into carbon dioxide. It would be nice if it's one step, and then it would be easier to remember. But it's like, this, does this. All right, so a couple more slides. I'm just going to talk about an acid and a base, and then we'll be done. Physiologic mechanisms keep the hydrogen concentration of body fluids in a range that is compatible with life. To sustain life, the body must maintain the pH of fluids within a narrow range of 7.35 to 7.45. So that's the range in the blood and tissues of the body, 7.35 to 7.45. And the body's going to do all kinds of things to try to keep that pH within range. What is an acid? It's a substance that releases a hydrogen ion when placed in solution. Some examples of an acid. I don't have any written in your notes. Can you think of an acid? Like a lemon. Lemon is very acidic. Isn't Coke really acidic too, Coca-Cola?
Yeah.
I've heard that if you pour Coca-Cola on your battery, it cleans all the
It does, I tried.
Yeah, you did?
I did actually have to do that.
All right, so acid, it gives off a hydrogen ion when placed in solution. And then to break that down even further, there's different types of acid, and we're going to talk about the volatile acid. When you hear the word volatile, what do you think of? Easily blows up. Yeah. Somebody has a volatile personality, they become angry and violent very easily, volatile. Well, a volatile acid is an acid that's in equilibrium with a dissolved gas. So a volatile acid will break apart and form a gas. Carbonic acid is a volatile acid. It separates into carbon dioxide and water. So because carbon dioxide is a gas, we can say that carbonic acid is a volatile acid. So anytime an acid can separate and form a gas, it's a volatile acid. And then there's fixed acids. A fixed acid is not in equilibrium with a dissolved gas. So any acids that don't break apart and form a gas are considered fixed acids. Therefore, the hydrogen ions of fixed acids must be buffered by bases in the body, or they have to be eliminated in the urine by the kidneys. So some examples that are listed there. The first one is untreated diabetes, and you have to write some notes next to it. With untreated diabetes, let me just give you a little bit of background. When the cells are not getting glucose inside, then they end up with a different type of metabolism in order to get energy. And the energy produces ketones, which are acidic. So somebody who has diabetes and the glucose isn't getting into the cells, they start producing a lot of ketones, and they go into a ketoacidosis. And when you see them in the emergency department, they'll have a history of diabetes, they'll be breathing really fast. I'll tell you the connection to that in a second. If you draw arterial blood, you'll see that the pH in their blood is really acidic, way below 7.35. because of all these ketones that are being produced. Well, when the blood is acidic, one of the things the body does to compensate for that acidic blood is to make you breathe faster and get rid of carbon dioxide. If you get rid of extra carbon dioxide, that helps bring acidic blood pH back to a normal pH. So So that's why they breathe fast. They're getting rid of CO2 to help balance that acid in their blood. All right, so what do you need to write down? For untreated diabetes, write down keto acids are formed. Keto acids, K-E-T-O-A-C-I-D. Keto acids. They're also called ketones. K-E-T-O-N-E-S, ketones. So keto acids would be an example of a fixed acid because ketones can't break apart and form a gas like carbon dioxide. So that's a fixed acid. The next one is lactic acid. And lactic acid is formed from anaerobic metabolism. This is formed from anaerobic metabolism. Anaerobic is A-N-A-E-R-O-B-I-C, anaerobic. So anaerobic metabolism. So if the cells can't get enough oxygen, then they still can produce energy, but then there's a byproduct that forms, and that byproduct is called lactic acid. So if you have a really bad cardiac output, your cells are like starving for oxygen. So what they'll do for energy is they'll have anaerobic metabolism, but they're going to start producing lactic acid from it. So if you have a patient with a low cardiac output and you draw arterial blood from them, you'll see that the pH of their blood is low. And it's low because of all the lactic acid that's being created from poor oxygen delivery. So anytime you've got somebody with low blood pressure, poor cardiac output, chances are you're going to see an acidotic blood gas. So lactic acid happens when you don't get good oxygen delivery to the tissues. The third one listed there is catabolism of proteins. When proteins are broken down, you get sulfuric acid and phosphoric acid produced. I don't have anything else to say about that. Just break down a protein. So if you eat a big steak or your hamburger from McDonald's, you produce sulfuric acid, phosphoric acid, but your body's healthy, so it has a way of getting rid of the acid, usually by the kidneys. So when these acids are in the blood, they will combine with bicarbonate. And what will happen is when you draw an arterial blood gas, and one of the list of things that print out from the machine is the bicarbonate level. And you look at the bicarbonate level and you'll see that it's low. It's telling you about the diabetic ketoacidosis. You're going to see a low pH in the blood. Well, you're going to see low bicarbonate also.
So all of these acids will decrease the level of bicarbonate?
Yes. So when somebody has an acidotic pH in their blood, the body's going to compensate by increasing ventilation. More carbon dioxide will be produced when these acids are present. I guess that bullet needs to be first, and then it shows you why. I can change it because you already have it in your handout. So you have extra acids. Extra acids will combine with bicarbonate. And now you've got a lot more carbonic acid. So when all that extra carbonic acid goes back to the lungs, you just blow off more CO2. And that's one way of getting rid of acid. So you've got all this acid produced in your blood and all these hydrogen ions. And what happens? Well, the hydrogen ions will combine with bicarbonate, form carbonic acid, And then when that goes back to the lungs, you'll exhale the carbon dioxide. And that's how you try to neutralize the pH in your blood. Which of the following is an example of a volatile acid? I don't know why some of them are yellow and some of them are white, so ignore that. Is keto acid considered a volatile acid? No, because they can't break apart into a gas, right? Can lactic acid break apart into a gas? No. What about carbonic acid? Yes, so C is the answer. And then what is a base? A base is something that accepts a hydrogen ion. So an acid gives off a hydrogen ion, and a base accepts a hydrogen ion. The ion will be negatively charged, called an anion. Another term that's used is alkaline. And soap is an example of a base. It has a very high pH, it's very alkaline. And I think that's a good place to stop. Talk about CO2 transport, what is an acid and what is a base.